All right, so here is the start of Unit 3 for us, Intro to Acid Base. Some of the stuff that I talk about today may be review, some will not be. For class, we are not going to be doing AP problems after this video. We are going to be practicing some of these techniques so that you are more prepared for acid base when we get to the more complicated stuff. So we're going to start by talking about strong acids and strong bases. You will need to know what a strong acid is and what the strong base is, because it will determine how that compound reacts with other things. Okay, so you're going to see a little bit about that in this video, and then we'll be going through that throughout the unit. If you do not recognize that something is strong or weak, you may be using the wrong reactions, etc. So it is important that you memorize your strong acids and strong bases. So group 1 hydroxides for bases are going to be strong. So you can see all of these group 1s are strong, or 1A, and by that I mean on the periodic table. For group 2, the lighter ones, meaning the ones at the top, because they have a lighter atomic mass, so the top of group 2 is not strong, not until you get to calcium, okay? So calcium, strontium, and barium are going to be heavier. And so those will be strong bases. For strong acids, there's really no way to kind of make this easier. You just have to remember them. Okay, so these are the 7 that you need to memorize as strong acids. And this has been, like, I memorized these when I took AP Chem. This has been a long-standing thing. You just need to know what the 7 strong acids are. So make sure you memorize that. There's not much I can do to kind of help you out with that. You just need to take some time and memorize it. So now I am going to talk about naming acids. And this is something that in class I will have a practice for you to do. This might be something you covered in honors chemistry. It might not be. Chances are, if you are a junior, we probably didn't go over it last year, but if you're a senior, you might have. It really depends on kind of it's not a required honors chemistry thing. It's one of those extra things that sometimes we throw in and sometimes we don't. So in order to make sure that everyone has it, I am going to go over it now. So there are 3 categories of acids for naming them. One is just going to be H and the element. One is going to be H plus a polyatomic that ends in ATE. And then another one will be a polyatomic that ends in ITE. So you can see automatically you need to understand and know your polyatomics in order to name acids. And of course, in AP, we've already seen that a lot of times you are expected to write out the reaction. They do not give it to you. So you will need to know how to name these things. So going from formula to name, if it's just H plus an element, we do hydro, the element name with IC, and then the word acid. So if it has hydro, it is not a polyatomic. If the formula is an 8 polyatomic, okay, so if you look at everything other than the H, and we see that this is sulfate, 8 becomes ic acid. So instead of sulfate, we have sulfuric acid. And then if we look at everything but the H and it's an ite polyatomic, like this is sulfite, ite becomes OUS acid. So when you're naming these, again, you're looking at everything except the H, and that will tell you how to name it. So here we have some formulas, and we are going to write the names for these. So PO4, you know, is phosphate. So that's going to be phosphoric acid. Because our 8 polyatomic is ic acid. Now, if we look at everything but the S here, it's just sulfur. There's no polyatomic there. So when it's just the element, remember you start with hydro, and then the element, you add the IC ending, so it will be sulfuric acid. Now, if you look here, we had sulfuric acid, but it was a different formula. The hydro is what tells you it's just the element. So hydrosulfuric acid and sulfuric are two different things. So here's some practice. If you want to pause the video and give this a shot and then come back and check your answers. So here we have just the P, so we know that's going to be hydro. Phosphorus will become phosphoric acid. NO3 is nitrate, that's the polyatomic, so this is nitric acid. CO3 is carbonate, so that becomes carbonic acid. And ClO2 is chlorite, so that becomes chlorous acid. Remember, the ITE becomes OUS. So now that we have going from formula to name down, we have to figure out how to write the formulas. So basically this is how it works. You look at the word and figure out what the anion will be, okay? What that everything but the H will be. Then you add enough H's to balance out the anion. Okay, so let's take a look. If we look at hydrobromic, we know hydro tells us it's just an element, and bromic means bromate. Okay, so the bromide ion is Br minus. What you're going to do is take a look at the charge, and that's how many hydrogens you have to add, because we want this to be a neutral compound. So if the charge on the bromide ion is 1 minus, we would add 1 H. So hydrobromic acid is going to be HBr. Now nitrous, we know OUS is the ITE polyatomic. So we have NO2, and that has a minus charge, -1. So again, we're just going to add 1 H. So we're going to get HNO2. So go ahead and pause the video, try these 3. And come back for your answers. So here we have hydro, so we know it's just an element. So F, the charge on fluoride ion is 1 minus. So that will become HF, that's hydrofluoric. Chromic is going to be chromate. You know that IC becomes ATE. I do not believe chromate was one of the polyatomics you had to memorize, but you can always look that up. So chromate is CrO4 2 minus. Because this charge is 2 minus, you need 2 H's to balance it out. So this is chromic acid. Sulfurous is sulfite, which is going to be SO3 2 minus. Remember, this means you have the ITE, so that's why it's not SO4 2 minus. Because this is a 2 minus, we're going to add 2 H's and get H2 SO3, and that's sulfurous acid. So this naming acids, again, you will have a practice worksheet on it in class. And it is something that I want you to be able to do, but it all starts with that polyatomic stuff. So if you want to take this time to review your polyatomics, that would probably be a great thing to do. Make sure you know them. So now we are going to talk about pH. Okay, we learned a little bit about pH in the last unit. We talked about what the formula is for it and all of that stuff. But now obviously we're going deep into acid base. So we're going to start talking more about it. Before we get to that, I want to talk a little bit about the logs of numbers. Multiple choice questions on the AP test do not allow a calculator. So you need to have a little bit of familiarity with how to do math in your head. Most of you are great with this. With the log, it's a little bit different because that's not something we usually do in our heads, okay? So what you want to take a look at is how the number that you're logging relates to the actual answer. So here you see the 1 times 10 to the 10. If you log that, you get 10. So same thing here, 1 times 10 to the third, you get 3. So whatever the exponent is, that's the number you are getting. Okay? So that's easy. If the number in front, like right here, these are all ones. Very easy to do. Okay? The exponent always relates to the number before the decimal point when you log something, okay? So the exponent of scientific notation always relates to the number before the decimal point. So what's going to happen if the number in front is not 1? So what you can see here is that if they want an exact answer, they're going to put it on open response. Okay, for multiple choice, you're really going to need to use some test taking strategies, which is why I want to talk about that now rather than putting it off. For multiple choice, you're really going to need to look at all your possible answers. And rather than trying to figure this all out in your head and do whatever you want in your head, you can look at the answers and rule them out based on the answers that you have. So you already know, like if this exponent is -3, then the number should be between 2 and 3. The number before the decimal point should be between 2 and 3, okay? What is the case is that this number, the number before the multiplication sign in the scientific notation, relates to the decimal places, okay? So the exponent always relates to this. This number always relates to this. Now you'll also notice that in the pH formula, it's negative log, right? So up here, we did log and we had -10 gave us -10. But here you see -1 is going to give you something between 0 and +1. -3 is going to give you something between +2 and +3. That's because we have the negative in front of the log symbol, okay? So -5 is going to give you something between 4 and 5, -6, something between 5 and 6. So with just that information, you'll probably be able to eliminate some multiple choice answers, okay? If you know that the exponent is -7, that means your answer has to be somewhere in between 6 and 7. So that's going to give you probably at least you can narrow it down that way. And then you can kind of look and see, okay, what happens this number to this? And you can see that the smaller this number is, the bigger the decimal point, the decimals will be. So 1.5 gives you 0.82, 2.5 gives you 0.6. So the bigger this number, the smaller these numbers are. Okay? So last thing I want to say, and I mentioned this before, is that for significant figures, if you have scientific notation, you only have to look at the numbers after the decimal point, because when we do sig figs for scientific notation, we're only looking at this, okay? So the exponent and the number before the decimal point, we don't have to count. All right, so here's some review from last unit when we talked about acids in solubility stuff, okay? So this is just a quick review about HF being the proton donor, the acid, the base being the proton acceptor, and then you have the conjugate base and the conjugate acid, which we'll talk about again. I'm going to review that for you. Okay, so this is the exact same slide we had in the last unit. And here is a weak base. So you have your base, which accepts a proton, your acid, and then your conjugate acid, which is your base with that proton, and your conjugate base, which is the acid without the proton. Okay? And this, of course, led us into a discussion of amphoterism, because acid could be either an acid or a base, and we'll get more into that in this unit as well. So here's a little bit about the conjugate acid-base pairs. The acid gives up its hydrogen and becomes the conjugate base. The base adds a hydrogen and becomes the conjugate acid. Okay, so that's a quick review, just so we have that kind of stuff there ready to go. Now we're going to talk about neutralization. A lot of what we talk about in this unit is going to be neutralizing either an acid or a base. The way you do that is by adding the opposite. So if you have an acid and you want to neutralize it, you add the base. If you have a base and you want to neutralize it, you add the acid. And what we're going to find out is how much do you need, okay? So what we're going to talk about first is just full neutralization. In full neutralization, we're going to have, it's basically just stoichiometry. We're looking at amounts of acid that we would need to neutralize base and so on, all right? That's what we're going to talk about in this video. When we start to get to less than full, that's something called titration. We will get to that. That is where the real work in this unit is going to be. So here's a problem that we're going to do. Calculate the volume of 0.034 molar potassium hydroxide required to neutralize 25 mLs of 0.05 molar nitric acid. Okay, first thing you need to do with these problems is figure out what your combination is. Is it a strong acid and a strong base? It is a weak acid and a strong base, or is it a weak acid and whatever combination it is, okay? So the ones we're going to be going over today always have one strong. We're going to save weak acid and weak base for later in the unit. So here, at least one strong, I should say. Here, potassium hydroxide is a strong base because it's a group 1A hydroxide. So this is a strong base, which I'm going to write SB. Nitric acid is a strong acid. Okay, so for this one, we're going to do strong acid and strong base. For strong acid and strong base, they completely dissociate in water. So the first thing I'm going to do is write the overall reaction. And that's going to be our potassium hydroxide plus our nitric acid. And that will give us water. Neutralization gives us water. And then we're going to take our potassium and our nitrate and get KNO3. Now, if you were to write this for net ionic form, okay, everything is aqueous and fully dissociates other than the water. So we would have K plus OH minus plus H plus NO3 minus gives us H2O, stays together. Then we have K plus NO3 minus. This, and this will cancel, and you'll end up with OH plus H plus gives you water. This is always the net ionic for strong acid and strong base. Okay, for strong acid and strong base, you always, because they completely dissociate, you always have that net ionic equation. So now that we have our equation, we can see that they're all 1-to-1 ratios. Okay, so we are going to figure out how much acid we have, and then we'll figure out how much potassium hydroxide we would need to neutralize it. So when I say how much, hopefully you understand I mean moles, but it should always be moles. So what we'll do is take the molarity and multiply it by the liters. And that will give us moles, which for this one, and I'm just going to write acid, but you can write HNO3 if you want, or H+, if you're using the net ionic. So now we need to figure out how much OH minus we would need to neutralize that, or how much potassium hydroxide we would need to neutralize that. Okay, so let's go through that. We know it's 1-to-1 ratios, but I'm just going to do it out to show you. So the moles of OH minus you would need, or you can do KOH if you're using the overall reaction, is going to be, we have this many moles of acid for every 1 mole of acid, we have 1 mole of H+. Okay, and that's because we have what we call a monoprotic acid. We'll talk more about that later in the unit. Monoprotic means 1 hydrogen. Okay, so 1 mole of acid gives us 1 hydrogen. But even if you don't know the word monoprotic, you can automatically see this because we've done this before with non-acids where we figure out how many elements we have in 1 mole of a compound. So then for every 1 mole of acid, we're going to need 1 mole of OH minus. Okay, so what that means, like I said, we knew it was 1-to-1, but I just want to show you how it would be done out in case it wasn't 1-to-1. So we need this many moles of OH minus. That's not what the question asks, though. The question asks calculate the volume. So the volume, if you have the molarity, is right here. So if you plug in your molarity of KOH, which was 0.034, you plug in the moles you know you need, you end up with this. Okay, there's got to be an easier way to do this, and luckily there is, okay? So if you don't know the kind of easy way to do it, you will just go through and do this. That's going to take you forever. The easier way is to just use your moles and volume formula, molarity and volume, excuse me. If you do that, you can just plug it in. If it's not monoprotic, we'll talk about that later, but this is a 1-to-1 ratio. KOH to HNO3 is 1-to-1. So we can just use this formula. So our molarity of acid is 0.05. The volume, I'm going to do it in liters, but you can do it in mils if you want. And then our molarity of our base and our volume. If you do that out, your volume of your base comes out to this, which is the same. So now let's try another neutralization. So this one is potassium hydroxide, which we know is a strong base, group 1 hydroxide. Nitrous acid is a weak acid. Okay, nitric is strong, but nitrous is not on that list of 7. So this is going to be a weak acid plus a strong base. And that does not have the same net ionic that the one we just did has. So let me explain why. So the overall reaction is going to be KOH plus HNO2 gives us H2O plus KNO2. But a weak acid does not fully dissociate in water. So when we go to write the net ionic, we do not break it up. So we can still break up KOH, right? That is a strong base. But the weak acid stays together. So then we have H2O, which still stays together, plus K plus NO2 minus. So now the only thing that cancels out is the K plus. So your net ionic is going to be OH minus plus our weak acid, gives us water, and just the nitrite ion. So this does give you a different, like I said, strong acid and strong base is always that net ionic. Unfortunately, as soon as you have one of them be weak, then you're going to have to do out the reaction, to do out the net ionic reaction, okay? So if it's strong and strong, nice and easy, H plus OH minus gives you H2O. If not, you have to do this all. So solving for the number is exactly the same as strong acid and strong base. So even though the reaction will be different, the actual work, we don't have to go through that whole process. We can just use our molarity formula like we did for the last one. So we'll talk about this in the next video, Ka and Kb. If you're given a Ka or a Kb, it doesn't matter here. As long as you have a strong base and or a strong acid. As long as one of them is strong, the Ka and Kb doesn't matter. So if you're given it, you can just ignore it. The reason for that is because if one of them's strong, so here we have a strong base, that's so strong, it's going to rip off all the H's from that weak acid anyway. Like, it's going to take care of that. So if we have that, we don't have to worry about what happens when it's weak and weak. Weak and weak, we care a lot about Ka and Kb, so we'll get to that later. So just an FYI, if you see that in one of these problems where one of them is strong, you can just ignore it. So here, we'll do the same deal. So we have 0.05 for our molarity of our acid. We have 25 mils of it. Oh, sorry. That's liters. And then we have a molarity of our base is 0.034 again. And so our volume of our base, not surprisingly, because we used the exact same numbers, is going to be this. Okay, so again, the only thing different here is going to be that net ionic equation. So let's do one more, and then I'll also prove why it works. okay? Because I won't bother going through all of the stoichiometry for this, but I will prove that it works when one of them is weak with this one. So here we have acetic acid, which is a weak acid, and barium hydroxide, which is a strong base. So same basic idea, except we're changing it to barium hydroxide. And that changes a little bit of how we use our formula, so we'll get there. First, I'm going to show you the overall and net ionic equations. Oops. All right, so that's the overall reaction. For net ionic, we would break up our barium hydroxide because that's a strong base. So we'll have Ba2 plus 2OH minus. Our weak acid stays together because remember acetic acid, which is weak, does not fully dissociate. Our water stays together. And then we can break up barium acetate. Now, this is not one of the solubility rules you need to know, but acetates are generally soluble. So I'm just going to tell you that. So for this, oh, sorry, I forgot to balance this first. So let's go back and balance this. I'm just looking at why it doesn't work out. So we have 2 OH minus here, and then we should have 2 H2O here. And then this would be a 2, and this would be a 2. Okay. So then the thing we can cancel out is our barium. So we have 2 OH minus plus 2 of the acetic acid. Gives us 2 H2O plus 2 of just the acetate. So our net ionic equation here does still look a little different, but especially since we have barium hydroxide, because that adds some 2's in there. So what you're going to want to do here is make sure you're careful, because each mole of barium hydroxide is going to give you 2 OH minuses. So when you're doing out your MV, you're going to have to factor that into it. Okay? So moles of acid, this is still a monoprotic acid because it has 1 H. So we don't have to do anything on that side, times volume of acid. Moles of base times volume of base times 2. Because on this side of the equation, you're getting 2 OH minuses for each one of those barium hydroxides. So you need to, if you add that times 2 on that side, you can use the same formula. So when you do this out, your volume of your acid comes out to this. So what I'm going to do now is kind of show you that this whole method works this times 2 thing by doing out the stoichiometry. So if I want to find the moles of the base, because we're looking to neutralize the base here. So if we want to find the moles of the base, we're going to do the molarity times the liters equals the moles. So we have this molarity times this many liters is equal to moles of base. Now we take that moles of base, for every 1 mole of base, we get 2 moles of OH, right? And for every 1 OH minus, we need 1 H plus to neutralize it. So that is going to give us this for the number of moles of acid we need to neutralize, okay? And this part right here, I will say, is always going to be the case. You're always going to have a 1-to-1. For every 1 H plus, you need 1 OH minus. That's always the case if you're doing out the stoichiometry. Because if we want H2O, because that's our neutralization, we have to have 1 H plus and 1 OH minus to add together to be H2O. So back to the problem. What we're going to do now is take this and figure out the liters. So we'll use our molarity formula. We have this many moles of H plus that we need over our liters equals this molarity. And so that gives us, for the volume of the acid, and that's the same that we had up here. So it does work if you just use your MA. MA is MV, MAVA is MBVB, as long as you remember to multiply because you're getting 2 OHs. Forgot the times 2 here.